The rest of this section, we're just going to classify different kinds of harmonic oscillators, starting with the undamped harmonic oscillator. So remember, for the 500th time, this is what our harmonic oscillator is going to look like, and it's damped if B is positive. It's undamped if B is 0. And that's what we're going to start with. Undamped harmonic oscillator, B is 0. And we know what's going to happen, right? We know what's going to happen. If you have no damping, the spring is just going to oscillate forever. The position's going to oscillate forever. It's going to look sinusoidal. The velocity is also going to oscillate forever. If the position is sinusoidal, the derivative is also sinusoidal, because we know the derivative of sines and cosines are sines and cosines. So we know exactly what's going to happen, but let's look at the math behind it. And we're going to show the qualitative analysis really comes into play more in the future videos, but we'll still show a little bit of qualitative analysis and show how this ties into what we've been doing earlier in chapter 3. So if it's undamped, then this is really the system that we're solving, or sorry, this is really the equation that we're solving, because B is 0. So using our shortcut method, we know that we have the equation ms squared plus k equals 0. It's going to give us a solution of e to the st. We know how to solve this, no problem. That's going to give us s squared is negative k over m. S will just be plus or minus the square root of negative k over m, which is just plus or minus square root of k over m times I. These are the eigenvalues. We know the eigenvalues are going to be purely imaginary here. There's no real portion. Remember back to 3.4 what that says about our system. Right? The real part, and again, this all goes back to Euler's formula. This is e to the a times cosine. Let's actually put a t here. It'll be e to the at cosine of bt plus I sine of bt. Right? If there's no real part, there's no exponential part. If the real part's 0, this exponential part goes out to 1. We get oscillation forever, right? We're not exponentially growing, we're not exponentially decaying. We know exactly what's going to happen. And that is indeed what happens for our simple harmonic oscillator. As a side note, this square root term over here is used extremely frequently, so we give it a special name. It's the lowercase omega, Greek letter. It's not a W, looks kind of like a W, but it is lowercase omega. And then we know what our solution is going to look like, again, using stuff that we know from complex, from 3.4. We know that our solution is going to look like, e to the plus, again, we only need 1, if you remember. So let's just use the positive omega times I, which again we know means cosine of omega t plus I sine of omega t. And then similarly, we have 2 solutions. So we can find our general solution by looking at a linear combination of those 2 solutions, and we'll get k1 cosine of omega t plus k2 sine of omega t, all stuff that we did earlier in the section and earlier in this chapter. That would be our general solution here. And again, we could find the vector solution very easily by looking at the velocity and doing that. Let's just do it, right? This is not hard. The derivative is just going to be negative k1 times omega sine of omega t. It's just the chain rule. Plus k2 omega cosine of omega t. And so if we know that if we were writing things as a vector solution, we get y of t. How would we write that? There's a couple of ways of writing this. How do I want to write that? Let's say k1 times cosine of omega t negative omega sine of omega t plus K2. And then it'll be sine of omega t. And this will be omega cosine of omega t. Like so. That's our vector valued solution. And again, we can see that again, both the position and the velocity are oscillating. They have the same period too, right? The period of cosine and sine are usually 2 pi. So our period here, which again, we're going to call the natural, well, our period, let's actually not introduce that term yet, right? Our period normally is 2 pi, but it's going to be 2 pi divided by omega because we're getting stretched, horizontally stretched. That's our period. So if you remember, a term that we used was the natural frequency. And remember, the frequency is the reciprocal of the period. So omega over 2 pi. Period is how long does it take to do a cycle. Natural frequency is how many cycles do we do per unit time. So that will definitely come into play as well. And again, we know that these are going to be ellipses. Maybe they'll be circles, but generally they're going to be ellipses. We could plot this. We could do this all by hand. But to save some time, let's just look at what we have right here. So here's our phase portrait in the YV plane. We see these ellipses depending on where initial condition is. If our initial condition starts here, we're on this ellipse. If our initial condition here, again, that's starting at the same position of 0, but starting at a smaller velocity, we'll be on this ellipse. And of course, if we start with no position and no velocity, we're in equilibrium. If you have a spring that's at rest with no initial velocity, of course it's going to stay at rest. Newton told us that. And you can see different solutions. If we have this starting value, that corresponds to, oh, sorry, I'm flipped. This starting value corresponds to this graph. Again, you can see they have the same period, that period of 2 pi over omega, just like we said. And again, the natural frequency will be the reciprocal of that. And they have bigger amplitudes. Whereas if your initial condition is over here, actually, let me make sure I'm doing the right initial condition. If your initial condition is over here, right, with a positive y value and a 0v, then you'd be over here. All right, that's pretty much it. That's what that looks like. And that is what undamped harmonic oscillators are, also known, remember, as simple harmonic oscillators. They're less interesting. It's kind of a special case. And of course, most situations in real life have friction. Most situations have damping. But if there wasn't damping, this is what we would look like. We just get oscillation forever, both in position and velocity. In the phase plane, that'll look like ellipses. If you graph them over time, they'll each look like sinusoidal curves. Next video, we start talking about 3 different kinds of damping. We've really only talked about one kind of damping, but we're going to say that actually damping can look a few different ways depending on how damped it is. Is something going to damp and still oscillate but eventually go to 0? Is something going to be damped so hard that it actually doesn't oscillate back and forth? And is there a third one? If so, what could that be? Wait and see.